pleased to introduce the speaker for this session, John Thomas. John is the founding president of M-Star CFD, overseeing all client support and engagement. Prior to M-Star, John was a research professor at Johns Hopkins University. He holds a PhD from Carnegie Mellon University and an MBA from Georgetown University. It will now be our pleasure to hear from John Thomas.
Hello everybody. I'm happy today to be speaking at Big Compute about GPU-based computing and physics-based digital twin of bioreactors. So just for some contextualization here, a bioreactor is a device used in biopharmaceuticals to grow many drug products. Many of the drug products used today are grown inside living cells, and a bioreactor is the device we use to curate that cell culture to maximize cell productivity and growth. There's a lot of interest in understanding what's going on inside those bioreactors, how we can optimize their performance, and how we can use physics-based modeling to increase yield and increase optimization of those processes. A quick introduction, M-Star CFD is a software company, and we develop physics-based modeling tools for scientists and engineers. And the purpose of those tools is to generate predictions, that is physical predictions, that are functionally indistinguishable from measured data. That is, if we're measuring or predicting, I should say, how a fluid moves throughout a vessel, we want our predicted velocities to match what would be measured experimentally over space and time. If we're trying to predict how some sort of bioreactor pH is going to change over time due to the addition of some sort of sparged gas or whatnot, we want to be able to predict to a T, that is to time, how those physics are going to vary over space and time. So we're not a correlation tool, we're not doing RANDs or some sort of steady state solver, as it were, fully transient, fully immersive, as it were, and real time. The company was founded in 2016. We have offices now in US, Germany, South Korea, etc. So it's grown pretty well. A roadmap for today, I'll talk briefly about CFD simulation, where it came from, why it's relevant, how we got to today. I'll show a little bit about how this type of software works, how we build these models, execute them, and the type of data coming out. I'll talk about some published applications with some clients, and then the application digital twins. And one of the points I want you to recognize here is that this idea of using GPU-based computing to develop digital twins and whatnot is not a direction or an idea. It's something that hundreds of companies are doing now. This isn't a pipe dream about, oh, maybe someday we'll be able to run these simulations and make them commercially relevant. People are already doing this. And the headline isn't this is new. The headline is if you're not doing this, especially in biopharmaceuticals, you're 5 years behind. Let's jump into it though. So how we got to today in terms of computational physics and modeling. A lot of this started with mostly computer science in the 50s, 60s, and 70s. And in that era, you would have researchers, PIs, world-leading experts try to solve specific physics problems using a tailored code designed to run on a specific piece of hardware. That is, you'd have some world-class researcher modeling some specific problem, as it were, and writing a code to run on some specific computer at his university or as part of his company or whatnot. Key players in this era were Los Alamos, Douglas Aircraft, NASA, of course. And again, they're trying to solve very specific problems. This was basic research. This was done by research groups. These project timescales are measured in years, if not decades. Hardware costs measured in today's dollars were tens to hundreds of millions of dollars, as it were. So foundationally, this era was born out of a period of first principles research. Coming into the 80s, 90s, and early 2000s, I should say, these codes and the hardware that came with them became somewhat commoditized, as it were. You could buy a commodity piece of hardware, as it were, and link it together. You could order that from a catalog. You could buy software that had GUIs wrapped around it to make it a bit more user-friendly, as it were. These softwares were designed to run on multiple CPUs, and they were general purpose, as it were, and they still are. You can run a variety of things. You can generally get a snapshot of maybe a flow field or a picture of what that simulation or that system might be doing. They're by no means digital twins. They're generating pictures for the most part in industrial settings. But this sort of advancement did reduce the barrier to entry. That is, you could have a subject matter expert running these simulations and have a couple of those at your company perhaps, as opposed to 20 years prior having one world thought leader doing one set of simulations, as it were. So there was some sort of democratization here, but even today, when people are using these kind of legacy tools, simulation run times and project run times and meshing run times are measured in weeks, realistically. People aren't cranking these things out on a 10-minute basis or whatnot. Which leads us to where we are today. In the last 10 years, there's been a fundamental shift in how we can compute and the algorithms we write for those computers. With the emergence of GPU-based computing, we're not even thinking about running on 10,000 CPUs anymore. We're trying to run on a few dozen GPUs. And the performance we can realize on those GPUs is orders of magnitude faster. And again, I want to make sure that point was clear. Not percent, orders of magnitude faster than what could be realized on a similarly priced CPU-based environment. And with this orders of magnitude, I mean tens, hundreds, thousands of times faster, becomes a fundamental shift in how we use these type simulations. Far beyond the idea of taking a picture of a bioreactor and looking at some sort of mean flow field and trying to shoehorn in some sort of blending analysis or whatnot. We're just modeling the physics in real time, as it were. Here's an example of some sparged bioreactor with sparging means gas bubbles are coming in, watching how dye is diffusing throughout, as it were. These simulations are running in real time. That means they run in, tens of minutes to maybe an hour, as it were. The setup time is tens of minutes, maybe an hour or so, and anyone can build them. That it means you can take your biologist out of the facility, as it were, and have him or her run these simulations to understand what's going on inside the bioreactor. You don't need to be a world's expert. You don't need to be necessarily an SME. You need to have good engineering chops. You got to have good scientific chops to understand what the code is telling you. But at the end of the day, this kind of completes the democratization, where in as much as you have technical insight, you can use these tools to augment your physical-based testing. And again, this is all made possible by advances in scientific GPU-based computing. And again, these hardware that I'll be running on today and demonstrating today, these are a couple of GPUs, and I'm running these simulations, again, as I mentioned, in minutes and hours, which is an important step change in what was done previously using RAND-based tools, specifically tailored to CPUs. And a quick little side comment here. People can take old code and put some of it on the GPU and realize some improvement, but really to best exploit these type of architectures, you've got to write a lot. You've got to write the first line of code and the last line of code, thinking about how a GPU computes, as it were. And having developed the software, at least speaking personally about M-Star, having developed the software in the era of GPU-based computing, it gives us some sort of blue water advantage because we're not trying to port over some 2 million lines of legacy code and hope some of it can shoehorn onto a GPU. We're running and writing from day one to fully exploit these massively parallelized environments. And that gives us a tremendous gain with respect to advancing this field and advancing the science in this area. Okay, so I talked a bit about how we got to today, from a campus computer to at least a commodity HPC, now to a GPU, as it were. Let's talk a bit about how this works. And let me just show you real fast. This is how these types of simulations work when you're running on a GPU. Let me cobble together a very simple example just to get an idea about how fast these run. Because we do a lot of bioreactors, I'll set up a little bioreactor here. I won't bother with CAD. I'll just load in some sort of little tank here. Let me go ahead and plop in some sort of little impeller here. You can imagine a biologist doing this. You can imagine a chemical engineer just kind of snapping the system together based on what she sees inside the laboratory. So maybe she'll go in here and put in some sort of, impeller, as it were, and change the impeller speed. And she might want to see, what sort of velocity profile she's going to get from this impeller on the bottom of the tank. So she'll go in here and add some sort of probe here and put this guy somewhere at the bottom of the tank. Let me go ahead and snap it down here, over here. Now, when she hits run, as it were, there's no residual minimization or correlation lookup, as it were, or some sort of, time averaging going on, right? Now, this is running on a pretty simple GPU. This is a laptop from Costco size GPU, as it were. And with that, if I go to post-processing results, I'm immediately getting data that mirrors what I'd see inside the laboratory. So if I go over here and look at some of these 2D slices, as it were, and I start pulling this data off the GPU, I'm not getting a snapshot. I'm running a numerical experiment, as it were. I'm actually watching these physics evolve throughout the vessel. I'm looking at what's going on at my probe over time, looking at velocity or whatnot, or position or strain or whatnot, or concentration. I'm making immediate comparisons to what I'm measuring inside the lab, and one better, seeing all the fluid mechanics, all the process mechanics that are driving those process outcomes. And you keep seeing me hit refresh here. I'm pulling this data off as it's being computed by the GPU. So I'm able to run these digital twins, as it were, in minutes, in a time scale that is comparable to how long it would take for me to set up this experiment and run it inside the lab. Whether it's 2D slices or 3D views, the data is incredibly rich. It allows me to kind of walk through the simulation and see how the physics are varying over space and time. Back to the main trajectory. Okay, so that's, that's the game here. When I can build simulations, run simulations, and post-process simulations that fast, it changes how I use simulations, as it were. When these become real-time experiments, I move away from outsourcing this to some CFD expert to give me some sort of mean flow field to me running the simulations while I'm doing the experiment and hybridizing that knowledge to get very good insights. Who uses M-Star? This is a small selection of firms with whom we've published or firms with whom we've given presentations. A lot of chemical engineering firms, a lot of pharmaceuticals, a lot of OEMs related to agitation equipment, bioreactors, etc. A fair number of universities, as it were. But most of people that use these types of tools are people that are doing process optimization and don't understand how they can increase yield, as it were, how they can get more growth out of a cell or whatnot, or how they can produce higher quality foodstuffs, as it were. And so that's generally speaking a lot of chemical engineers, mechanical engineers is kind of where we land. Let's talk about published applications with some clients. Again, one of the biggest applications of a tool like this is understanding process scale-up. So process scale-up in almost any chemical engineering parlance describes taking an invention at the lab scale and scaling it up to production scale, going from a milliliter sized reactor vessel to something that might contain, gee whiz, 20,000 liters, if not more. And so understanding how those physics vary across scale is one of the key steps to understanding how to scale these processes up. And it starts with the small stuff, that is having very good models for understanding what's going on inside your bench scale system, how they blend, how the bubbles rise, what strains you see, how homogenized, as it were. That's the first step in reproducing that environment at larger scale. So step one, where most of our clients use these types of tools, is make digital twins of their lab scale equipment to understand what environments are realized there in an effort to replicate them at larger scale. And again, at larger scale, you can do these same types of simulations. This is with a different client. This was a Bristol-Myers Squibb. But this is a much larger bioreactor now, where we have much longer scale physics in terms of impeller speed, bubbles rising. I'm showing here oxygen accumulate inside the vessel, as it were. But understanding how these cell culture environments change across scale and how we can keep those physics constant across the scales is a key step in drug development. That is, so many good products die on the way to production because we can't solve the scale-up mystery. With a tool like this, it becomes immediately clear. Looking at other types of applications in terms of blending and whatnot, getting two different fluids mixing together. This is a different digital twin development with AbbVie in this case. Again, examining how you can optimize your reactor performance to look at blend time or whatnot. Again, these aren't pictures in the sense that this is what the simulation gave us. These are pictures in the sense that this is how the simulation advanced through time. And this ability here to model and generate results that look a lot like an experiment. These are actually simulation outcomes here, but you can compare apples to apples to what you're seeing inside the lab. Gives you a lot of confidence in terms of corroborating what the simulation is telling you and trusting it when you're trying to apply it for systems where there may not be that apples to apples validation. But this ability to watch and take pictures in a way that immediately mimics what you're seeing inside the lab, very compelling from a validation standpoint. There are other papers as well we can speak to should people be interested in that, related to droplet dispersion and other sort of complex where witches brew, courtesy of the US DOE. And again, one of the most compelling things here is when people do ridiculously simple tests and show that a tool like this works. Like, here's a ridiculously simple test. if I throw some tracer particles in a vessel and I watch where they go over time using some four-dimensional tracking instrument, does a tool like M-Star reproduce what I'm seeing inside the lab? And the answer is yes, routinely. That is, we can accurately predict using these GPU-based algorithms the time evolution of the flow field, the spatio-temporal variations in the flow field, as it were. And again, make these apples-to-apples comparisons between what people are doing inside the lab and what they're able to measure with a tool like this. And it's all brought to you by, drumroll please, GPU-based computing. Because we can run these algorithms so efficiently in a GPU-based environment, we can make predictions that, quite frankly, are non-tractable using conventional finite volume-based approaches or legacy CFD software. And again, here's kind of the real point, and I wanted to make sure this sticks, is this isn't like a incremental improvement. That is, GPU-based computing, especially for computational physics algorithms, like if you're claiming a 10% improvement as we went to the accelerator, you're doing it wrong. Like if you're claiming, well, our process times decreased by 50%, you're doing it wrong. Like if you're correctly running a physics-based code that is born and bred to run on a GPU as it were, you should be seeing orders of magnitude. I mean, here's apples to apples again. This is a research fellow at Delft looking at bioreactors and cell growth. When he runs these simulations, using in this case M-Star, of course, on a GPU, he can predict about 1 second of bioreactor mechanics with about 80 seconds of wall time on a pretty simple single GPU. When he does that same analysis, as it were, on a 10-core pick-your-poison CPU-based system, as it were, using finite volume-based approaches, you're talking tens to hundreds of thousands of seconds per second. Okay, again, this isn't like a 2x speed increase. It's orders of magnitude. And when you have this step change, it fundamentally alters the types of problems you can ask and the type of insights you can get. CPUs versus GPUs. This isn't, Burger King versus McDonald's, as it were. This isn't Coke versus Pepsi, as it were. This is Boeing versus shoes. Okay, this is spacecraft versus a rowboat, as it were. And that's kind of exciting in terms of the physics it allows us to access. And let's talk about some of these current applications. Again, here's an example of full process control. So we are modeling here, as it were, and this is a kind of a whole HVAC type application. The release of some sort of toxic gas coming from underneath the hood. We're modeling how the sensors are recording the time evolution of that dissolved gas, as it were. And we're then monitoring how those sensors, through a PID controller, are going to inform the gas flow through the HVAC system. We're monitoring how that gas flow is dispersing the gases, the dissolved gases, as it were, throughout this room. This is all happening in tandem. Like these aren't, well, we did a flow field, then we put some scalar in there to watch how it moved, and then we ran 10 of those to see kind of how different airflow conditions make it move. No, we are doing this numerical experiment on the fly, as where all the physics are coupled as they would be in nature, as it were. And that kind of fidelity, unprecedented. Carrying on to this sort of physics here. Here's more of another suspension process where we have particle-laden flows and we have a control loop that's dynamically adjusting the impeller speed in order to realize the target process objective, which is to get all these particles off the bottom of the tank to accurately get some sort of buffer concentration. The exact physics are important and the application are important, but what's more important is the principle here. Is we are running simulations that are so far beyond pictures of a flow field and some sort of estimate of how a blob or particle flow field is evolving through space and time. We're mimicking an entire process, not just the fluid mechanics, but the control logic around it at the end of the day. That is how this PID controller informs impeller speed, again, to achieve this target objective. This is way beyond, as it were, your dad's CFD. Last but not least, again, going on to these multi-phase type systems, again, the ability to model these bioreactors, see how we can tune their operation to realize tailored environments, as it were, see how we can let the computer figure out, for lack of a better word, what sort of operating conditions it should have, rather the system should have, to realize tailored cell growth conditions. It's pretty cool. And what allows us engineers to do here is optimize processes in silico as a way to augment and minimize the amount of physical testing we need to do. Okay, let's bring this baby home. We've moved way beyond finite volume-based CFD. We moved way beyond correlation-informed modeling, as it were. We've moved way beyond this idea of, well, I'm going to do a CFD campaign and I'm going to, mesh this thing and we're going to get a team on. Like, this process has been democratized. Anyone can build these things, and the questions they can answer and ask in minutes and hours is ridiculous. As I mentioned earlier, this isn't a direction or, well, wouldn't it be great if someone tried to commercialize this, or, hey, wouldn't it be neat if in 10 years we could do this? This is now. In fact, if this is news to you, you're 5 years, 10 years behind, as it were. And as time goes on, these GPU-based compute models are becoming increasingly indistinguishable from measured data. That is, when I'm measuring how this bioreactor is going to behave and put a probe in there and compare my probe measurements to my simulation predictions, as it were, if I put those two down on paper, you'd have a hard time telling who was who. And this idea of the GPU-based digital twins changes how we use these tools. That is a step change in the types of questions we can ask, the step change in the types of questions we can answer, and it's really neat to see the continuing emergence of this hardware inform how we as engineers pivot from physical testing to digital testing using these really exciting digital twins. Thanks for tuning in. If I were in person, I'd solicit questions. I'm not, but you have my email. Reach out, call. I'm happy to talk about any aspect of this. We can go deep. We can go shallow. We want to talk about the nature of turbulence mechanics and the Kolmogorov length scale. Let's go, buddy. You want to talk about, what a PID controller is and what a bioreactor is? Give me a call, chat about it all. But at the end of the day, it's really exciting stuff. And thanks again for tuning in.